balloon is rising at a constant speed of 5 feet per second. So, got my balloon that's going up in the air. So the distance has gone up, I'm going to call that h. If I'm giving the speed for that, that is what? What variable would that be? dh dt is 5. A boy is cycling along a straight road at a speed of 15 feet per second. So if the balloon's going up, the boy is riding down here. Maybe if I can draw a person. So if I call that my x, that would be our dx dt is 15. When he passes under the balloon, it is 45 feet above him. So what's happening is the boy is right here under the balloon. Okay, and this is a height of 45. But then the boy rides off and the balloon keeps going up, right? So it says, how fast is the distance between the boy and the balloon increasing? So I'm looking for this side, let's call it y. So I'm wanting how fast that's changing. I'm looking for dy dt. 3 seconds later. So this height was 45. I know that the balloon rises 5 feet every second. So in 3 seconds, how much does it go up? It rises an additional 15 feet. So altogether, the height of this balloon is 60. The boy was right here. He's riding for 3 seconds. We know that he's going 15 feet per second. So in 3 seconds, how far has he traveled? 45. So we're looking at the instant when the height is 60 and his distance is 45. We'll probably need our y, but could we find the y for that particular instant? We did Pythagorean theorem. So 45 squared. So at that instant, the y is 75. These three numbers are all changing. The boy's moving, the balloon's moving, so the distance between them is changing. So none of these things are a constant. So if we set this up, we have to do the derivative. Derivative of x squared would be 2x dx dt. Derivative of h squared is 2h dh dt. Derivative of y squared is 2y dy dt. So then if we plug in, the x was 45, dx dt is 15, 2 times 60 dh dt was 5, equals 2 times 75 dy dt. Divide, and dy dt should be 13, I believe. I do want units on this. So look here. Y was a distance, and this, our distances were measured in feet. T is time, we are measuring our time in seconds. Is that one okay with everybody? Next question we had was number 6. So a linear approximation question. Our function is the square root of 7 minus x. So I'm going to write that as 7 minus x to the 1/2. we're looking when a equals -2 and we're approximating the square root of 7.1. So the linear approximation, that's the L of x. We need an equation for it. The equation of a line requires a point and a slope. To get my point, my a is -2. If I plug a -2 in here, 7 minus -2, I get the square root of 9, which is 3. So my point is -2, 3. Now we need the slope. How do we get the slope? We have to do the derivative. Slope of a tangent line is the derivative. So, f prime of x, 1/2 comes down, inside stays the same, subtract 1 from the power, times the derivative of the inside, which is -1. A negative power, we put it on the bottom, so we get a -1 over 2 square root of 7 minus x. We need the slope at the point when our a is -2, so if we plug in a -2, 7 minus -2 is this a 9, square root of 9 is 3, times 2 is -1, 6. So now I have my point and slope. That's what we need to write the linearization, the L of x. So if we plug into y equals mx plus b, our y is 3, m is -1, 6, x is -2. Subtract 1/3 over and we get 8/3. So if all I asked for was the linearization, it would be -1/6 x plus 8/3. Now you can use that to approximate any square root that we need. I asked for the square root of 7.1, so we have to be careful. Am I just plugging a 7.1 in here? No, because the original was the square root of 7 minus x. So you need to find out what x has to be. In other words, 7 minus x has to equal 7.1. So in this instance, our x is a -0.1. So that's what we are plugging in. So if I put that in, we get 2.6833. Questions on that one? The next question I had, number 7. So another linear approximation. And this time I didn't give you a function. Told you I want you to approximate 83 to the 3/4 power. So if you think about it, this means the 4th root of 83 cubed. Okay, so my function would be what? The 4th root of x cubed, or you could write it as x to the 3/4. My a has to be something close to 83 that we could evaluate. So think about something close to 83 that you could do the 4th root of. 81. Okay, so if we plug this in, our point, 81 to the 3/4, so the 4th root of 81 is 3, to the 3rd is 27, so there's my point. I need my slope. So we have to do the derivative of this. So f prime of x equals, exponent comes down, subtract 1 from the power. And if you want to rewrite this, the negative just puts it on the bottom. So it would be like this. We need that slope at the instant when our x is 81. So the fourth root of 81 is 3 times 4 is 12. 3 over 12 is 1/4. So that is my slope. I have a point and a slope. So now we can write the equation. So plug into y equals mx plus b. If I subtract this over, like 27 over 4, is that right? So the linearization is 1/4 x plus 27 over 4. If all I asked is for the linearization, that equation is your answer. But I asked you to approximate 83 to the 3/4. So what am I plugging in for my x? 83. And we get 27.5. You know, if you want to check how accurate that is, you could easily type in 83 to the 3/4 power. And that's 27.49847, so we're pretty close. Questions there? Number 8. So we have y equals the natural log of x plus the square root of x squared minus 1. I want the differential. What is the differential? What am I asking for? dy. Couple ways you could do it. You could think about this. The derivative of y is dy dx. The differential is just dy. So essentially it's like you do this derivative and then you just multiply that dx over. Okay, so my final answer will be dy equals something. And it's just the derivative and we multiply that dx to the other side. So if I want to do this derivative, keep in mind a square root is like a 1/2 power. Okay, derivative of a natural log is what? 1 over the argument. So that's the derivative of the natural log piece, but we have to do the chain rule. So times derivative of the inside. So I need to do the derivative of this mess. So derivative of x is 1 plus, for this square root, the 1/2 comes down, inside stays the same, subtract 1 from the power, times derivative of the inside. Derivative of x squared minus 1 is a 2x. Have I lost anyone there? We can clean this up a little bit. A 1/2 and a 2 would cancel. So we have this times, here we have 1 plus, that negative would put that on the bottom. Not a whole lot we're going to do to clean this one up. You could certainly distribute and combine like terms, but it's not going to make much difference. So if you left your answer like this, that's okay. You have to have the 1 over x plus, you could write this as a square root or 1/2 power. Then I have this one. And you just multiply that dx over. So the differential is just dy. And all it is the derivative times dx. So really, just like derivatives we've done before, the only difference is how you write the final answer. Any questions there? On number 10, I had somebody ask about part C. Do we need to go through any other parts on number 10? Ask now. If I'm going to do part of it, this will be the time to do any others that we needed. So 10C wants the velocity. So I need the velocity formula. Remember, velocity is just the derivative of your height, so the derivative of the original, this is what you did in part A, was 15 minus 3.72t. I need when the height is 25 meters, so I'm plugging 25 in for my height, so in the original. Okay, it's a quadratic. We always set quadratics equal to 0. So I'm going to add over my 1.86t squared, subtract my 15t. Now obviously on the test, if you don't have a calculator, I'm going to have to give you a nice pretty equation here or a graph or something. But on study guide you do have a calculator. How could we find this? Could look at a graph or the quadratic equation. Say either one. Let's do the quadratic. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So if I plug this in, I get 5.71 when I do the plus, and when I do the minus version of this, I get 2.35. So I asked you the velocity twice, going up and coming down. Which of these times will be going up? The 2.35, because you started on the ground. So you throw your rock up, it's obviously going to go up faster than it comes back down, right? The first step is going up. So you're going to take that time and plug it into your velocity. And we get 6.258 meters per second. Notice that is a positive. Why is that velocity positive? Because it's going up. So this one should be negative because it's coming down. So I plug the 5.71 into my velocity equation. And I get negative 6.2412. Is that okay? Problem 11. A company makes computer chips from square wafers of silicon. It wants to keep the side lengths very close to 15 millimeters, and it wants to know how the area changes when the side changes. Okay, so if I'm asking how the area changes, if I want to know how something is changing, what am I referring to? A derivative. Okay. Find a prime of 15 and explain its meaning. So we know we have oh, that is a really bad square, but pretend it's a square. What do you know about the sides of a square? Are they x and y? They're the same. Okay, so it's talking about a of x, so my sides are both x. So I want to know how the area changes. So let's talk about that. Area of a square, length times width, is just x squared. So we want a prime of 15. So a prime, the derivative of this would be 2x. So a prime of 15 is 2 times 15, which is 30. So that was the first question. A prime of 15 is 30. Explain its meaning. Remember, a derivative tells you how it's changing. So when the side lengths are 15, we were in millimeters. The area, is it increasing or decreasing? Increasing because it's positive. By 30 square millimeters. And that's all that one was wanting us to do. Find a derivative and just interpret it, really just recognizing that a derivative is how something's changing. We've done a lot of those, talking about like cost and marginal cost. You know, I give you a cost function and ask you to find the derivative at a certain point and ask what that meant. And it told you, you know, when you're producing 5 units or whatever, the costs were increasing by a certain amount. So just trying to get you to recognize that a derivative is the rate of change. Is that one okay? Number 12. When is the tangent line horizontal? When do you get a horizontal tangent line? What's going on when that happens?
There's no slope.
Right, the slope is 0. How do we find the slope of a tangent line? Derivative. So here, all I'm asking you to do is set the derivative equal to 0. So we have to start on the outside. Big thing here is the square. So our derivative, 2 comes down, inside stays the same. If you subtract 1 from the power, now it's just to the first, so you can leave that off. But we have to do the chain rule. So if you work your way in, now we have to do the derivative of that. So a derivative of a natural log is 1 over the argument. Chain rule one more time. Derivative of the inside. What's the derivative of x plus 4? 1. So this gives me 2 natural log of x plus 4 over x plus 4. There's our derivative, and we want that to equal 0. Alright, bringing back your algebra days. What would you do first? Can multiply the x plus 4 over. Those cancel. 0 times anything is just 0. Then we could divide by 2. Alright. What do I do from here?
E to the 0 power equals x.
Remember, a natural log is a log base e. So if we change this to exponential form, that means e to the 0 power equals x plus 4. Anything to the 0 power is 1. Subtract your 4 and x is negative 3. I asked you for the point, so that's when my x is negative 3 if I wanted the full ordered pair. If you plug a negative 3 into the original, the natural log of 1 is 0. So the point on the original is also negative 3, 0. So that question, I was more just wanting you to practice the derivative of a log. So that's more my emphasis there than the actual solving that equation. But okay. Number 13. Equation of the tangent line to this curve. So, equation of a line needs a point and a slope. I gave you the point, you need a slope. How do you get the slope of a tangent line? Derivative. Okay. Derivative of x squared is 2x plus the derivative of 4xy. You have to think of this as a 4x times a y. We have two variables, so we have to do a product rule. Derivative of 4x is just 4, so derivative of the first times the second, so 4 times y plus the first, 4x, times the derivative of the second. Derivative of y would be dy dx. This was our implicit differentiation, which we were also doing when we did those related rates. Every time we did the derivative of a variable, we put d something dt. If it just has x and y, then the x do its derivative like normal, but a y gets a dy dx with it. Plus derivative of y squared would be 2y dy dx. Derivative of 13 is 0. Okay. We have a couple options here. The slope of the tangent line is the dy dx. So I can either solve for dy dx and then plug in my point, or I can plug in my point first and then solve. Do you guys have a preference? Plug in first? Probably be easier. So my x is 2, y is 1. So 4 plus 4 is 8. 8 and 2 is 10. So dy dx is negative 4/5. That's my slope. have point and a slope, we can write the equation of our line. So y is 1, m, -4/5, x is 2, plus b. Add my 8/5 over. So our final equation is y equals -4/5 x plus 13. Any questions on that? The next question we had was problem 15. So find dy dx. So if we do this derivative of y is dy dx equals, I have to treat this as a product. So derivative of the first, derivative of x is 1, times the second, plus the first, derivative of the second. Derivative of the natural log of y would be 1 over y, and it needs dy dx every time you do the derivative of a y. Plus derivative of x is 1. I have dy dx in both of these, so I'm going to put them on the same side. Here, what could we do? So that would leave me with 1 minus x over y. To get dy dx by itself, you would divide. Final thing I might tell you, is it really proper notation to leave a fraction in a fraction? No. The quick way to get rid of that is just to recognize that this denominator is y. So if I take top and bottom times y, then we get y natural log of y plus 1 times y is y, over on the bottom 1 times y is y minus x over y times y is just x. And so that is my final answer, if I clean it up all the way. Is there anything you want specific practice over? I mean, I can just make up some problems and give them to you if we have a few minutes. Like number 5, you guys know how to find the maximum error. That's just talking about like your differential. So you guys can do that. Practice one. Okay. Let's say, since you guys didn't ask about number 5, I'll make up the problem. So you know it's going to be pretty if I'm making it up. Let's say the radius of a ball was 4 inches with a maximum error, or with a possible error of 1/10 of an inch. You weren't very accurate. Let's find the maximum error in volume. Okay, so if I am looking at this, my radius is 4. If I want the error in my radius, what do I represent that with? dr. I want the error in volume, so I'm looking for dV. Right, if you're talking about a ball, that's a sphere, volume of a sphere, I would give you that if you needed it, is 4/3 pi r cubed. Yes, ma'am.
Is this the only type of problem that you don't put it over like dt?
Yes.
Okay.
And you'll notice, like on the problems where you need the dt, when you're looking at the derivatives, it won't just say like the error is 0.1 inch. It'll say inches per second. So when that derivative is a rate, something per minute, something per second, that's when you put the dt with it. So if we do this derivative, dV equals 4/3 times 3 would be 4 pi r squared, and the r gets a dr. So then we can plug in. So that's 16 times 4 is 64 times 1. 64 pi, volume is cubed. 0.1, thank you, 6.4 pi cubic inches. Are we okay with that? Let's see, do we need another? The implicit differentiation stuff.
We do either 6 or 7 of those.
So something like one of those?
Yeah.
Okay. Let's approximate the square root of 63. So what would my function be? Square root of x, or x to the 1/2. What a would you use? That has to be something close to 63 that you can do the square root of. So 64. The ordered pair then would be 64 comma 8. You just plug it in. We need a point in the slope. So my slope, if I do this derivative, 1/2 comes down, subtract 1 from the power. So it's 1/2 square root of x. So to get my slope, I plug in the 64. So I get a 1/16. Y equals mx plus b. So my y is 8, m 1/16, x is 64. 64/16 would be 4. So our y-intercept is 4. So the equation is L of x equals 1/16x plus 4. So if I just ask for the linear approximation, that's it. But what do I need to do now? Plug in a 63. So again, on the test, I would have to give you something pretty nice for you to be able to plug it in here, or I might just say set it up. I wrote 64, that's a 63. So 1/16 times 63 plus 4, and we get 7.9375. Quick check, the actual square root of 63 is 7.93725, so we were really close. That's okay. Do we need like derivatives of logs? You guys are okay with those? What if I said if I asked you to find this derivative, what do we have to do here? Product. So derivative of x is 1 times the second plus the first derivative of the second. So derivative of a log is 1 over the argument times derivative of the inside. Derivative of 1 plus x to the 4th, or sorry, the square root of 1 plus x to the 4th. So keep in mind that's like 1 plus x to the 4th to the 1/2. I'm not going to have enough space. So the 1/2 would come down. Inside stays the same. Subtract 1 from the power. And derivative of the inside, derivative of 1 plus x to the 4th is 4x cubed. Okay. 1/2 and 4 would give me a 2. X times x cubed is x to the 4th. Okay. We have a 1 over the square root times, this is a negative 1/2, which is also like a 1 over the square root. When you multiply those together, what happens? The square roots drop, so it's just over 1 plus x to the 4th. I know my work was very sloppy there because I ran out of space. Did I lose anybody? If I ask for the differential of this, you know, this is just like dy dx, that's the derivative. If I ask for the differential, what would change? Yeah, it would be dy equals all of this times dx. So differential is just like a derivative. You just move the dx over. You did okay on like 14, implicit differentiation using trig functions. That one was alright. Remember your derivatives of sines and cosines. So you have like a position function. The derivative of position is velocity. Derivative of velocity is and I think we're probably done. But if you guys have any more more questions, please don't hesitate to come see me. Can we clean the desks, please?